Hi, everybody. I'm Stacy Dees, the RASC-AL Program Manager, and welcome to the first of two pre-briefings for the 2018 RASC-AL Special Edition Mars Ice Challenge. The purpose of these pre-briefings is to share some of our existing knowledge with you so that you're in the best possible position to submit design concepts that build on the successes and failures of the water extraction methods currently being used by the space drilling community. We call this building on the collaborative success. Today's briefing is designed to provide you with relative context for the Mars Ice Challenge from NASA's perspective, as well as to provide you with some of the lessons that we learned in last year's 2017 Mars Ice Challenge. Before we introduce today's presenters, let's get to know the rest of the RASC-AL program management team. All of us hail from the National Institute of Aerospace. Starting with our leader, Shelley Spears. She serves as the RASC-AL Program Director. And unfortunately, Shelley is unable to make it today because she's in the air on travel, but sends a very warm greeting to all of our prospective Mars Ice Challenge teams. Victoria O'Leary serves as our Program Support Specialist at NIA. And Ania Cotton is a Hampton University intern who is working with us in support of the RASC-AL program. From NASA headquarters, we have Bob Collin, a program coordinator for the Science Mission Directorate. And I'm going to turn the mic over to Bob now, who will introduce today's presenters. Bob?
Thanks, Stacy. Hi, everyone. Our first presenter joining us from NASA headquarters, Science Mission Directorate in Washington, D.C. is Rick Davis. Rick is a sponsor and champion of the Mars Ice Challenge. He currently serves as the Assistant Director for Science and Exploration, conducting extensive integration work between NASA's Science Mission Directorate and the Human Exploration and Operations Mission Directorate on deep space policy, including Mars exploration policy. Rick also co-leads a joint study to identify potential human landing sites on Mars using current assets, as well as define future reconnaissance needs required to support human surface operations on the Red Planet. Hi, Rick.
Hey, Bob.
Joining us from NASA Langley Research Center in Hampton, Virginia, we have Dr. Chris Jones, a RASC-AL sponsor, as well as a co-creator and judge for the Mars Ice Challenge. Dr. Jones works in the Space Mission Analysis Branch, and his current work includes strategic analysis of space technology investments and mission design for an Earth science satellite. Hi, Chris.
Hello, everybody, and hello, Bob.
Also joining us from NASA Langley Research Center is Dr. Bob Moses. Like Chris, Dr. Moses is a co-creator and judge for the Mars Ice Challenge. Since joining NASA in 1989, he has contributed to the agency in a number of ways. Most recently, Bob joined a small blue sky study team to derive a strategy for using in-situ resource utilization, ISRU, to enable crewed missions to Mars by the 2030s. Hi, Bob.
Hey, Bob, back at you, and Rick and others. Thank you for allowing me to join you today.
And just a reminder, feel free to ask questions for the presenters in the live chat feature on our YouTube page, and we'll answer them during the stream. And with that, let's jump right in. So over to you, Rick.
Okay, everybody, it's really wonderful to be here with you. As Bob alluded to, one of the things I do here at NASA headquarters is that I co-lead an effort to pick where we're going to set up the base on Mars. And that's a multi-year process because there's so much we don't know. But it's a really cool one. And I'm going to try to give you a little bit of a feel for that and try to give you a sense of why this ice challenge is potentially so important even to that process. And before I get into that, I would like to say a couple things. You know, about 20 years ago on the internet, you did not have to be like have a PhD in computer science to actually make a major contribution. And I would just challenge you as you're thinking and learning about this, just realize that with Mars, it is so new. It is like the internet about 20 years ago, where we are really looking for new and innovative and creative ideas. And NASA as an agency by itself is not going to be able to do this all by itself. It's going to be working with international partners, commercial partners, and academia to actually try to figure out how you go do this really audacious thing. And so we really view this ice challenge as a way of getting ideas from the community. And when Stacy stresses the importance of building on the lessons learned from last year, we really mean that. We want to build on those lessons. We want to build on everything that we've learned and try to give that to you as succinctly as we can so that you can run and actually help push the ball a little further down the field on this really cool problem. So with that preamble, I'd like to kind of talk a little bit about NASA's goals. So NASA getting to Mars is really the stretch goal. If you look at, how, and we've been in space 17 years right now. If you look at how the computers have ballooned in terms of their capabilities, what they had in, say, 1961 to what we have right now today, Mars is really our stretch goal as a society, and I'd even say as a species. And so it's an exciting one, but it does need, you almost have to have a tremendous humility to understand what you don't know and go figure out how to go do it. And so a lot of times we think of there's a distinction between robotic and human missions, but really, if you're doing Mars, you have to really think of them as very symbiotic. The robotic missions are paving the way, but then eventually the humans get there and they'll take it to the next level. But they're going to be there just like all of us have a bunch of computers with us all over the time. It's going to be the same thing with our robots when we get to Mars. And so really they go hand in hand just like they do here on this Earth. Now I'd like to talk a little bit about the human landing site study. You'll see a concept. What we did is we started this about 2.5 years ago. We were actually put out a request for what we call exploration zones. Those are really a 200-kilometer diameter circles where we were asked for all across the planet for ideas about potential exploration zones that gave us amazing science and also gave us the resources that we need. And by resources, principally, I would say that that is access to water resources, which you'll see more how that ties in a moment. We also have an amazing fleet, and I'll show you a picture of it in just a moment, at Mars right now that is providing a ton of information about the planet. One thing that people don't realize, we've been at Mars for 50 years with robotic spacecraft, which is an amazing accomplishment in and of itself. And it's not just the United States, it's a whole bunch of internationals are there too. And so we have a lot of data. And so one of the reasons we wanted to get going on this process right now, one, because there was so much we didn't know, but two, we want to use that fleet. And I'll show it to you again in a second. Secondly, by getting going, as Bob alluded to, it actually teaches us what we need in terms of new data and new satellites going down the road. And so as we learn more, we're refining that, which will help and guide our future investments in terms of satellites. On the next slide that Bob just called up, we actually see the fleet that we have at Mars right now, and it's really amazing. It's not just, as I said, the Indian Space Agency has one, the European Space Agency, along with Roscosmos, the Russian Space Agency, has an orbiter there. And really, it's becoming a very international thing. And all of those satellites and those amazing rovers, with Curiosity being the latest edition, and we've got another one called Mars 2020 going in 2020. We're launching that. And they're teaching us a massive amount about the planet. And you can see some of the other future missions on that chart. Go to the next one, please. So this is the idea of an exploration zone. I mentioned it already. It's a 200-kilometer circle. We're finding that this really works well. And the idea is that the human beings would be, you see a little white box there, and that's essentially the habitation zone, but that's where they land. That's where their habitation module is, their lab modules. That's where their power supplies are. But then we have this 200-kilometer diameter circle, which with the rovers that we have under development right now at the Johnson Space Center, which are really amazing things in and of themselves. We believe that we can get out to 100 kilometers either way. That's a 200-kilometer diameter circle. And really, we needed something to bound where we were looking for both cool science places and those water, principally, but resources in general. You know, the next one. And then, so we put out this call about 2.5 years ago. As I said, we actually got 47 proposals by 45 teams, really literally from all over this planet, and they cover an extremely wide region of the planet. Every one of those little circles that you see there represents one of those exploration zones to scale. And really what we learned is that there is amazing science. Like this concept works, amazing science can be there, and there is water there, and I'll talk about those in a little bit. We purposefully restricted we didn't want to go too far north because it gets extremely cold at Mars if you go really far north. So we went to plus or minus 50 degrees latitude. And then we also restrict how high up it is. The fact of the matter is you need to be somewhat low down the environment to actually have enough atmosphere to help you with braking and slowing the spacecraft down. So that a lot of those constraints are on that page. If we go to the next page, please. So an exploration zone. So when we did the lunar missions, we actually went to different sites. I think what exploration has taught us, particularly really long distance exploration, we've done a ton of it as human beings. Antarctica is a tremendous example. They really tell you that the way we did it maybe at the moon was worked for what they were trying to do, but really if you're trying to do sustained presence, you really need to think about a semi-permanent base. That is actually what McMurdo Station here is. It is a semi-permanent logistics node, and then they actually push out down to the South Pole research station, or they go to other research locations, but they have a base where they can build up spare parts, you can build up food, all the things that human beings need to survive in really harsh conditions, and you can get it in there and leave it there so that it's needed when the bad days arise. And if we go to the next slide, please. This is not the only time we've learned how to do this. On this next slide, you'll see that we've been exploring for ever. And Jamestown, Quebec City, International Space Station are all examples of this idea of a logistics node, where if well chosen, Quebec City and International Space Station, I'd say were well chosen. At Jamestown, maybe not so, since it's now an archaeological dig. But the point being is that they really were the places where not only did people launch out from to go further and explore, but they allowed people to build up the supplies they needed to do it and to extract resources. Next slide. And really, I now want to focus a little bit on the resources piece of this, because that's really crucial to what you're going to be doing. If you had tried to explore the American West like we are currently exploring space, it would look like this ridiculous cartoon that we're showing, where you are carrying water and food and all that stuff with you. That is not the way successful exploration is done. It is fundamentally about living off the land. And at Mars, there are a ton of resources. We already know that the most intriguing, again, is water. And so let's talk a little bit about water. We show a bunch of different feedstocks. We know that there are essentially buried oceans and glaciers at Mars. We know that there are what we call hydrated minerals, which are basically gypsums and sands and rocks that actually have water molecules locked up in them. And then you've seen in the news recently things like recurring slope lineae, which we don't totally understand, but many believe that they may have a strong connection to water. But in general, there's two broad categories. There is the water molecules that are locked up in soils, or regolith as we call it, and then there are the subsurface ice ones. Now, let's see. So let me talk a little bit about the challenges of those that we have right here. With hydrated minerals, we really have, we can see them from space, but we don't really know how wide the field is. With the spectrometers that we use, we can sort of see that they're there, but we don't know the depth, we don't know the density, we don't know the concentration. So there's significant knowledge gaps that we have to overcome. We actually thought we saw a field with one very promising hydrated mineral, and we sent Curiosity to go look at it. And with the resolution of those cameras, we really couldn't find it. That's one time, really, if you're trying to validate the existence of these resources, you'd have to actually have a campaign, which we are seriously trying to figure out how we might go to. Subsurface ice is really the cool one that developed. Maybe we learned it about 10-ish years ago, and we've seen where we've actually landed Phoenix, which was much further north. But you scooped and you can see the ice. We've seen impact craters that slam into it, and they reveal ice there as well. That's pure water ice. And then we have a radar on the Mars Reconnaissance Observatory that actually sees these oceans. Now, one problem we've had there is that radar the way it was designed to look for liquid aquifers that were way deep, and the frequencies they chose to use were designed for that purpose. That's actually not what we found. What we found were these frozen oceans and glaciers and so forth. And unfortunately, with the frequency range that we have, there's a blind spot in the 0 to 10 meter range that is really fundamental, and we're working to close that down. But that is fundamentally a key point. And we do expect those oceans and glaciers, we expect them to taper off as you go south and it gets warmer. It's simply that the ice would sublimate over time and models there. But what we don't really understand is the taper function because of that blind spot within that 0 to 10 meters area. So for picking a base, I would say most people who are actually working on this problem right now, you really think it rotates on the availability of these two water feedstocks. And really, what you get is there's 4 gears, as we call them here, if you will. The 4 fundamental questions that we're trying to figure out. One, is it really there? So in those hydrated minerals, when you get a spectral hit, do you really know that it's there? Is it a field you can rely on? Can you send a ground asset like a rover to go validate it? Or with the ice, subsurface ice, we can't see that 0 to 10 meters, which is probably exactly the region we need for in situ resource utilization, and which was our code word for using water, for human use. And so there are fundamental gaps in our knowledge there. The second question you have is how can you produce it economically? And so really what you're doing is actually helping us probe that critical area, because what we need to know ultimately is the mass of the equipment needed there, the power levels that are needed, and the operational complexity from using it. And so subsurface ice is one area that we really haven't looked at very much. And so your work that you're doing actually really can help us figure out that problem out. That's why when Stacy talked about building on the lessons of the past, we really stress that because we want you all to really run with this and actually help us try to figure this out. The third question that's really important is just how much water are we talking about? When we did our first workshop to pick where we're going to send human beings, we ran some rough numbers that actually indicated 100 metric tons. And the big thing you're doing is filling up the Mars ascent vehicle with methane, and you need the hydrogen and water to actually do that. But you're also eventually talking aquaculture or agriculture purposes or hydroponics. And so really getting a good understanding of how much water we need is a third area that's really critical for understanding this. And finally, the next question is, since the Mars ascent vehicle is probably going to be the first thing that really uses a lot of the local resources, namely water and oxygen, you really want to make sure that if you head towards more northern sites, which is where the ice is, or more southern sites, that you can actually launch from that site and get up to the Mars transfer vehicle, which is what the ride that the crew has to return home. And so we have to run studies on that. We've run some, but we have a lot more homework to do on that. And you also want to protect for abort situations to make sure that when the crew, and maybe you'll be on the crew, that you can actually get off there in the bad day if something really bad goes wrong. Go to the next slide. Lastly, I have just a couple other additional points. And this is a special region. So I want to spend a little bit of time with it because there's actually some questions that we ask in the proposals about this. So I wanted to introduce this concept. So we worry, one of the coolest things about Mars is that you might actually find life there. And how cool would that be, is to be able to do that. There have been plenty of movies and they're actually getting at the core theme. We don't really, if it exists there, we don't understand the nature of that life. And so there's a couple pieces here. One, we want to make sure that the water is usable, not just chemically, but we also want to make sure that if there's a biology in there that we know it. And so, and secondly, we want to protect the crew. And so anytime you start accessing regions where there could potentially be life, those become questions for OCRA, and we call those regions special regions. So I wanted to make sure you had that terminology firm in your minds, because it's a really key question that has to be looked at as we look at using water to make Mars missions possible. And really, Bob, that's pretty much all I want to do. I would say is that if you want some more information, we have our website right here. And secondly, we have a distribution list, and it's a great way to learn about Mars. And we would love to have you send us an email here, and we'll be glad to add you there, because it's a great way to learn too as you prepare for this challenge. And we wish you all the best of luck. Thank you.
Thanks, Rick. I did have a follow-up question. I was wondering, how do you balance the need to be in southern latitudes for so it's not too cold, with the fact that most of the subsurface ice is farther north? What does that end up doing to our base selection?
So let me, it's a great question. Let me just clarify a little bit, because when you said southern, I think you meant equatorial.
Yeah.
So equatorial, the advantage of equatorial sites is that they are, they're warmer. You know, on a warm day, you know, you get up to basically freezing, and then at night it drops like 120 degrees Fahrenheit. It gets pretty cold. You go further north, just like on our planet, it also is the warmest temperatures are going to be colder. Although the summers, you know, get pretty warm there, and they have real seasons there. And so that's a trade we have to look at, because if you're down here where it's warm, the problem is there's not subsurface ice there. At least we haven't seen it. And so you're using the hydrated minerals, which, you know, that has its challenges. The fact of the matter is that on this planet, we don't produce water by squeezing it out of rocks or soil here. And so that suggests that that may be challenging at Mars, where you're power starved. However, if that's the only way to do it, then human beings are pretty creative and they'll figure it out. The ice is there, and one of the big things we're trying to do is figure out how far that ice goes south, which is really your question. And so we're doing a lot of work there, but because of that 10-meter range that we talked about, where we have a gap in our knowledge, we don't really understand the taper, and therefore we're really working to understand just how far. I mean, you have to know that taper function to actually be able to figure out how far south you can go. Hopefully that answers your question.
Yeah, and thank you very much. And I would just like to remind everyone watching to ask any questions you have in our YouTube live chat, and we'll answer them to the best of our ability. And now we're going to turn things over to Chris and Bob. So if Chris, you'd like to get us started.
Sure thing, Bob. Good afternoon, everybody. And again, what I'd like to do is take a little time to tell you about some of the lessons we learned in doing this ice challenge for the very first time last year, or rather earlier this year. We've also got a couple of photos included here that Bob Moses took for us that show what some of the ice looked like even a couple of days after the competition ended, to give you an idea of what you might expect to be dealing with. So with respect to lessons learned, there's really 7 that jumped out at me that I wanted to talk about today. The first is that the interaction of the regolith with the ice, that interface where those two meet, turned out to be one of the bigger challenges that teams encountered when they were getting down into the ice. Moving through the regolith itself wasn't as big a deal, and once they got to the ice, they generally had a pretty good idea. But because of the fact that some of the ice began to melt and mix with the regolith, it made for a very muddy mixture that proved challenging to deal with. So keep that in mind as you're working on designing your concept and your concept of operations. The second is there's a really important need to do integrated testing before you actually get to the competition. For some of the teams, that day before the competition started, when they were setting up their equipment, was the first time they had brought all the pieces of their system together. And even if the system works flawlessly in each of its individual components, bringing it all together always drives out some issues or bugs that then teams found themselves scrambling to try and fix there at the competition. So make sure, and I think we've built this even into the requirements for this year, make sure to bring together your system, test it out, and get used to all of the mechanical and electrical and computer elements interfacing with each other before you actually show up on competition day. The third is there's no one right way to do this. We had 8 teams earlier this summer, and each of them brought something different to the competition in terms of the nature of their water extraction system or how they processed what they were pulling out of the test bed. And there's definitely no one correct answer that anyone has proven just yet. So be willing to try out new ideas, be willing to research interesting ideas, even those that go beyond what you might think is the default way to do this. The fourth is we've got part of the competition where we're looking to see, can you operate your system autonomously? That added another level of challenge and another degree of difficulty, even beyond the hands-on operations that feed into the first few lessons I've talked about. The autonomous operations really removes your ability to intervene from there. And oftentimes it was those interventions that helped teams get unstuck from having a drill bit starting to catch in the regolith, for example, or being able to move their system to a different location because they didn't like the hole they were already drilling in. So in order to really do well in that autonomous section, which is a great opportunity to score points, and also is an important thing to us at NASA, because that's probably how we're going to go about trying to do a lot of this water extraction, is without direct human intervention. Be prepared for that to be just as big a challenge as building the system in the first place. Along those lines, and getting back to some of the other lessons, a fifth lesson that we took away from this, and that a lot of teams from this past competition remarked on, is the importance of a diversity of skill sets in their team base. It's not enough just to have, say, a collection of mechanical engineers who are very good at putting together systems that can operate mechanically. You're going to need expertise in electrical engineering to make sure that you've got all of your power and fail-safes operating correctly. You're going to need somebody who's got a strong background in computer science or computer engineering who's able to help with developing the interfaces you use to drive the equipment as well as the software that helps govern it. It can be useful to bring in industrial engineers, systems engineers. Some teams use concepts that probably benefit from having chemical engineering. So be prepared to expand out and look for a variety of disciplines and skill sets, because that's going to make your team a lot stronger, and that will prepare you for your future career in engineering in the real world, where it takes all of those diverse skill sets to come together to make a project like what we try to do at NASA to go to Mars work. The sixth is that due to the nature of the test stands, there's a tendency for some of the regolith to collapse down into the holes that are being drilled for those teams that are drilling as it gets down into the ice. Some of the pictures on these subsequent slides, and Bob, we can go ahead and click through to one of those, show that even for teams that had very strong performance here, this is a snapshot that you're about to see of the winning team and the ice blocks that they had. There was still dirt that fell down into there, and as a result, the water that they extracted tended to come up fairly cloudy. Some teams, in fact, wound up with what they were able to find, almost had a very muddy sludge there. So whether you want to try and figure out a way to prevent that in the course of initially drilling your holes, or you want to deal with it by building a better filtration system, be prepared for the fact that you're not going to be interacting just with pure ice and then pure liquid water. Instead, there's going to be regolith mixed in, and finding a way to deal with that is going to be a challenge. Finally, the last lesson that I want to give you guys is that the soil itself is fairly loose. This may not be exactly like what you're going to see on actual operations on Mars, but for these test beds, many of the teams didn't even register a weight on bed or find much resistance moving down through the regolith until they got to that ice interface. So be aware of that as you're going through getting your experience testing, and even as you're doing your initial system design. So the graphic here and then is showing one team that dug down into a hole on the hole on the right is the hole that they drilled on the first day. We're looking down into the top ice block, and then the hole on the left is what they drilled the second day. But to talk a little bit more about that and some of the other lessons learned, I'd like to turn it over to Bob Moses.
Okay, thanks, Chris. That was a really good assessment of lessons learned and the 7 things to kind of look out for. Regarding this photograph, I want to just point out that the hole on the right, that is about the diameter of their drill bit. The reason the hole on the left is bigger is they continue to work through drilling and not really assessing what they were doing, to the point that they were really melting the ice near the top of the block and making a slurry. And that's something, as Chris mentioned, you really don't want to have to deal with. Their hole on the right-hand side was smaller. It was a little tighter around their drill bit, and they were able to get down to the next block of ice, and they had some water to extract and to and it was a good day the first day. The second day was not so good because they worked the ice, melted it, and made a slurry that they had to deal with. So again, I can't stress that enough. One point I'd like to add as to why we're using ice blocks beneath the regolith rather than trying to use hydrated minerals for this test. We've done enough studies to know that we're going to need a lot of water. We're going to need a lot of water, not just as consumables for the crew or for radiation protection, but as propellant. The propellant we would like is methane, but hydrogen is certainly available as well. But both of those, both hydrogens, the only hydrogen source there is from the water in the ice pack that we think will give us the amount of volume of water that's necessary for the least amount of energy to extract it. So that's why the test setup that you're seeing involves blocks of ice beneath a little bit of regolith overburden. There was a chart that Rick showed earlier of all the landing sites, but it also showed on there the percent of water, and also it showed areas where we know there are frozen lakes beneath just a foot or so of dirt. So that's really our starting point on all this, to see if universities can come in and have some fun with this concept. And again, it's not trivial. We had 8 teams show up, and they were pretty confident day one, but by day 4, they realized they had they had learned a lot, and there would be a lot of changes they would make going forward. And we're happy to share those with you as much as we can.
So Bob and Chris, is a question for you guys. In Antarctica, they actually do Rodwell holes, where they drill down, and then they leave an ice overburden. They get down into the ice and they leave it so that structurally, it's actually got a layer of ice, and so that it helps prevent the regolith or dirt, if you will, from collapsing in on the thing. Do you have any thoughts about that in terms of that applicability, and whether or not that can even be explored in this kind of a challenge?
I've got a couple of thoughts. Chris, do you want to go first?
Sure, I'll start. So the Rodwell idea, or Rodriguez well, is definitely one that we're thinking about more here on the NASA side of things. If we can find a large enough ice deposit on Mars to set up a Rodwell as has been used in Antarctica, there's definitely a lot of potential there to then extract a lot of water by volume from that. I'd like to hear Bob's thoughts here on especially how feasible it might be to do that with the setup that you'll be encountering at the competition.
Yes, so this competition is going to be, I don't want to give away any of the secrets on what they need to bring and address the first lesson learned that Chris mentioned that needs to be a precaution in the design. But the one thing to remember about Mars is you don't have the atmospheric pressures at sea level like you do at Antarctica. So there's another reason for looking at how you would cap off or seal off around the drill bit once it gets into the ice, so that regolith doesn't come in to the hole. And certainly maintaining contact of the bit with only ice at all times, or whatever your contraption is, if it's mechanical, seems like a really good way to do that, or seems like a good objective to have. And certainly the Rodwell concept does that. There may be other concepts as well that would allow the extraction of water affordably in terms of energy without having to deal with a slurry. So.
Thanks.
We do have a couple questions coming in from the live chat. Aero Zumba fan asks, are there any concepts you would urge us to stay away from, things that didn't work well last year? Let's you want to take this one, Chris?
Sure, and then Bob can add on if he can think of anything I've missed here. again, given that this was our first time doing this competition, there's nothing that's an absolute definite, no way it's going to work. That said, there were some things we saw that definitely looked like they were encountering a lot more challenges. One team was looking at essentially trying to scrape away the regolith overburden and then go down and extract the ice directly. They ran into some mechanical challenges getting that system to work, and there's also the issue with that being a challenge with respect to sublimation when you try and put that into effect on Mars. So I don't know if that concept worked as well as some of the other concepts that were being proposed around. Bob, what do you think?
There were a couple of concepts. That's one of them, Chris, for sure. There was another one that was bringing in a working fluid, and they had trouble getting the working fluid in. And so there were just issues with going with complicated, a more complex system. And I understand that next week you're going to have on a Hangout probably one of the best persons on the planet to talk about water extraction on Mars. And I'm excited for all the teams to have a few minutes to talk to Chris Zachnig about what he has been struggling with and trying to design a system that he feels confident that once it's placed on Mars, it's going to work well without any humans there to help. So, but yeah, there's some penalties there intrinsically for coming up with a complex system with too many moving parts. And you really don't know that you've entered or crossed that threshold until you start doing the end-to-end testing that Chris recommended everyone do, every team does before they show up for the competition. So test and test your concept as much as you can, even on a block of ice. You can go down and buy a block of ice somewhere, but test it. So.
Bob and Chris, maybe you can comment to this. I mean, so one's a comment, second is a question. Get your thoughts. So the first one is that, on the surface of Mars, it's basically like being at 110,000 feet on an airplane. And so it's a very low pressure environment. So sublimation is really something you got to think about in that environment. And secondly, Bob talked about it, but I just want to stress, I came out of the ops work. I worked in ISS and the space shuttle for years. And I'll tell you, when I previously mentioned that the things you want to know about equipment, there's power, and there's massive equipment, and then there's operational complexity. Bob is doing a really great job of stressing that point. I just want to emphasize it and see if he has any other thoughts. Operational complexity, these systems may have to operate by themselves for extended periods of time. When crews are not there initially. I personally believe we'll get to a permanent basis, but initially that is not going to be the case. These things are going to be put down, and we're going to be counting on them to generate propellant and water that can then be used for propellant and other uses. So really, you don't want to you want to keep it simple. There's that sort of principle called KISS, keep it simple, stupid. But it's a joke, but it actually gets at the very core point, which is that if you keep it simple, it's going to have that robustness that's really needed in a design in this kind of a harsh environment. Bob or Chris, y'all have any other comments you want to add to that?
I've got one. I will say that there's quite a few engineering disciplines represented among the 8 teams, and the teams that had a little bit of experience or knowledge about mining seem to have done pretty well. So I encourage everyone to any team that's going to compete and apply to this to do some homework on the mining terrestrial, and there's some stuff on extraterrestrial mining as well, some concepts. But please do your homework and do some calculations before you start buying things and going down a certain pathway.
Anything you want to add to that, Chris?
The only thing I would add is to reiterate what Rick and Bob have said, which is that simplifying your operations really does bring a lot of benefit to the table. One of the things that in the research we're doing at NASA that we're finding is going to be a challenge is we need systems that are going to be highly reliable and highly capable of operating without human intervention. It's a tough challenge, so we're not expecting that we're going to see the perfect solution just from doing this. But if you can figure out a way to balance that simplicity with the ability for people to not have to intervene, and that's kind of the point of the autonomous operations part of this, that's a real kind of advance that's going to be very useful to us going forward. So it's definitely an important thing to think about.
Thank you very much. We actually had another question come in from Max Parks. Were there any novel ideas last year that maybe didn't work at first, but you think have potential to be successful with more development? Why don't we, Bob, you want to take?
Yeah, gosh, I don't want to give away too much because I do want some innovation without plagiarism for this next team coming in. But there was some attempts to include some heating elements and other things in there. And, you know, there's something to consider. But again, every little bit that you add in complexity is going to cost you somehow. So if you are thinking of some of the way that, you know, you're looking at mechanical, but then maybe also looking at some type of heating or whatever, thermal, be sure that your concept or mousetrap is going to work well when you start combining these things. Don't just assume that the way that you're going to do it for this test is, well, you don't have to do it for how it would be on Mars. So this is just going to be a walk in the park. I assure you it will not be if that's the mentality that you bring to the table. So please do your homework and test.
Chris, anything to add?
I just echo a lot of the things that Bob just said. There's certainly a number of interesting ideas there that I'd hate to give away the secrets for because those teams will probably be trying to build on them. But getting back to the point I made earlier, there's definitely no one right way to do this. So there's approaches that might be described as sort of the default way you might think of doing it, but those are not definitely shown to be the correct way. So feel free to go out there and experiment, especially when you're still in your initial concept development phase. Try out some different things there, but then make sure you're doing your homework to really make sure that the system you do select, you have gotten a good job of getting it integrated together.
Thank you very much. And we had another question come in from Alejandro Trujillo. He says, thanks for doing this. Power, budget, and time allowed to operate. When will we hear more about this? That might be a question that Stacy could answer, or Bob or Chris, who wants to go first?
I'm going to defer to Stacy.
Okay, so this is honestly something that we had not worked out. There were initial talks with Tesla, who was considering giving us some power walls and having the systems operate off of the power walls. However, due to the catastrophic events that have recently happened in Puerto Rico, a lot of Tesla's Powerwall capabilities and their team has all been sent to Puerto Rico. And so we hadn't been able to finalize that yet. Tomorrow during the question and answer session that we have with the judges, which I'll tell you a little bit more about that in just a second, but we're going to address some of that tomorrow. So definitely make sure that you tune in to that question and answer session. And we'll also have those answers regarding power written out on our FAQs after the fact. So I'm sorry I couldn't give you a whole lot more information right now, but it will be addressed by tomorrow.
Just a bit of a follow-up. Should they be designing with the Mars power environment in mind? If they get bonus points, if they bring their own nuclear reactor?
I don't know if the NASA safety folks would allow us to have the nuclear reactor in the hangar next to their expensive planes. But definitely, we are operating on limited power, limited access to energy on Mars, obviously. And so at a minimum, you will be limited to a 120-volt battery at 10 amps. And it might That's probably about the minimum.
If I might add to, you know, at Mars, we've said it, mass, power, and operational complexity. You know, it is extremely expensive to deliver a kilogram of anything to Mars. And so that's part of the reasons why we're trying to use local resources, is because it's so expensive. So really, anything you can do to minimize the mass, minimize the power, and increase the operational robustness of it by probably sticking to, you know, simplicity of design, but there are lots of other ways to achieve that, or ways to help accomplish that, is just good. I mean, that's sort of at a high level, but really that's the game, is you were trying to reduce mass, reduce power, and yet at the same time have a balance with operational simplicity. I mean, Bob or Chris may have other thoughts on that too.
Nothing for me, just agreement.
Anything you'd like to add, Bob?
No, I'm good, thanks.
Well, with that, it doesn't look like we have any more questions coming in. So I think I'll turn things over to Stacy. And oh, well, we just have one come in right now from Carolyn Morin. How do we balance development of a system that would work well in Mars conditions with performing well in the competition? Chris, why don't you start us off on this one?
All right. It's definitely a challenge because there are going to be two very different environments there, and we're looking for you to address both. We're still finalizing the exact details of the scoring for this year's competition, but one of the points of emphasis is to be able to see very clearly what your path to flight is for this system to operate on Mars. We really do want to know what would you have to change about the system you brought to the competition in order for it to actually function at the low temperatures, at the low pressures, in the dusty environment, all the additional challenges that come with Mars that you're not going to have to deal with in the hangar at NASA. And the scoring is going to reflect that. So I would definitely say that while having a good system that can perform well in the competition field is still important and is just plain fun to build, it's also going to be very important to focus in on what would it take for that system to actually operate in the Martian environment. And I think you'll see that as some of the other documents and guidelines come out in the coming days and weeks.
Anything you'd like to add, Bob?
Yes. Think of it this way: the ways that you might melt, say, a refrigerator ice that's jammed up, your freezer. Yeah, there are a number of ways you can probably think of as a way to get that ice melted and out of the way. But those aren't going to work on Mars. They really aren't, because you got sublimation. So it's really, we're really asking you to take a step back and look at this thing from a practical way and imagine how it might work on Mars. Given that you can't count on the atmosphere to help you, it's going to hurt you. Certainly defrosting a refrigerator, the water's going to drip there and you can get it out with a number of ways. But that's not going to work well on Mars. That ice may not even be there, and you may not even be able to get it into the bottle. And if you can't get the water into the bottle then and be used for the benefit of the mission at Mars, then there's no way that will be sustainable. So again, it's just stepping back and thinking about the constraints, just the engineering constraints that the atmosphere, the regolith, the fact that Mars is so far away, like Rick said, and the kilograms are going to cost to get there, and just be very clever. Spend a lot of time thinking and planning and bouncing ideas off each other. And I cannot stress enough to the idea of walking down the street to another department and ask some students there if they were doing this, how would they do it? The more minds and the more diverse the minds, the more likely you're going to end up being a winner or a second or third place on this. So again, do your homework, talk to people, lay out, understand the constraints, and then start working in your trade space.
You know, and I'll just add to what Bob's saying. You know, It's not just winning the competition, but frankly, this is such a new area. You may help us figure out how to do this. I mean, and so, you know, it's, you actually, you know, there's just not, you're like you're on a frontier. I mean, kind of jokingly say that, but I mean it. You know, there are no playbooks here. And so what's really fun about this is you're helping create it. So thank you.
All right. And unless there are any more last minute questions, I think we'll turn things over to Stacy to close us out.
Thanks, Bob. So you've heard this
Stacey?
already from each of our presenters today, and I'm going to make one more statement about the importance of the integration and testing prior to coming to the competition. Not only is it important, but it's actually required this year. And so we're actually going to have you submit proof of the integration before you're even allowed to show up at NASA Langley Research Center next summer. So as you're preparing your project plans and you're thinking through your timeline that you're going to include, definitely make sure to include in your timeline that integration and testing. And so I just, as we're wrapping up, wanted to make you aware of 2 more events that we have in the coming week for the Mars Ice Challenge. The first is a question and answer session with the judges tomorrow. And so we'd asked for some questions in advance, and we've already received a good number of questions. And at this point, they've already been sent to the judges, so we're not going to take any more advanced questions. But when you dial in tomorrow, which the question and answer session is actually at 2 p.m. Eastern Standard Time tomorrow. And when you dial in, we're going to address those questions that we received in advance first, and then we'll open it up to any additional questions that you may have. So definitely make sure, take advantage of that opportunity to talk directly with the judges. You can ask questions of any type of nature. They can be technical in nature, they can be programmatic, whatever questions that you have. And then this time next Wednesday, so 1 p.m. Eastern Time on the 25th, we're going to have our second and final, probably, pre-briefing for the Mars Ice Challenge. And as Bob Moses mentioned to you earlier, that pre-briefing presenter is going to be Dr. Chris Zachney, who's probably the nation's, if not the world's, leading expert in terrestrial and extraterrestrial mining, ISRU. He's fantastic. He has a great presentation for you on some of the different types of drills that they use, some of the different water extraction techniques that they've used in various climates, and what they're learning about Mars through the testing that they're doing at Honeybee Robotics. He's been working with NASA for a really long time, and I think as you are doing your research, you're going to find that a lot of the papers, books that you're going to research are actually going to be written by Dr. Zachney. So we really do encourage you to tune into that and to just benefit from his expertise. It really is an awesome experience for you, and we really encourage you to take advantage of that. And with that, I want to thank our presenters today and thank all of you for attending, and hope you have a great week. We'll see you next week.
Thank you.